Hello, thank you for your interest in the mechanical subteam of the Duke Robotics Club. Here's a little bit about what we do. The mechanical team is responsible for designing and building almost all the physical structures on the robot. Perhaps the most important of these is the main frame. This is the part or assembly onto which all other parts of the robot are mounted. This frame, of course, needs to be strong enough to support all the required loads, and it needs to support the components in such positions that the robot as a whole floats and floats level, so that no power to the thrusters is required to keep it in the desired orientation. We also design and build all the actuators the robot has to interact with its environment and score points in competition. Of course, the stack is also a key part of the robot since it houses all of the electronics, and the mechanical team is responsible for very reliably waterproofing the stack so that water never gets in to ruin the electronics. And we build the internal structures in the stack that keep the electronics in place. Finally, after all the design is done, we fabricate the main structural frame and all of our actuators, or manage the fabrication from an outside vendor. The mechanical team goes through the same basic design cycle every 1 to 2 years. That cycle starts with researching what has been done in other AUVs, such as the ones shown on the slide, which were created by universities from other states and even other countries for competition in RoboSub. After that research, we do some ideation, building off other teams' ideas as well as our own team's ideas from the past to create many possibilities for new robot designs. And we select the best of those designs using an objective decision-making process. Finally, once we have a design selected, we'll hone in on the details and fabricate it in the following months. The mechanical team tries to keep our ideation process as creative as possible and our idea selection process as objective as possible. As shown in this first image, we start, after doing our research, by creating a large number of diverse ideas about what our next robot could look like. We then screen out the infeasible ideas, like some of the ones shown here, and we score the remaining good ideas in order to determine which will be the absolute best for our final robot. Before we're able to do the final scoring, we discuss at length the design criteria that we're considering, and we might even do a mock-up and print some of the designs to make sure everybody's on the same page and help us make good decisions about how to design our robot. The criteria we use to evaluate different proposed designs and decide which are the best change a little bit year to year, but some of the core ones are shown on this slide. The robot, of course, has to be able to support all of the features that the electrical team wants to include, such as having a permanently mounted stack or having a removable battery capsule. Then it's super important for us that we can actually manufacture the robot we design, that it's going to have full use of all 6 degrees of freedom possible underwater, that it's going to be durable, it won't break when we use it under normal conditions or under extreme conditions like impact. We also want the robot to be modular so that if we have, for example, a new actuator design, we'll be able to replace the old actuator design with the new one without making major changes to the structural frame or other parts of the robot. And in general, we want to keep the robot as light as possible, just because that scores a few extra points at competition. Our design and build cycle usually takes 1 to 2 years, and the changes we make can be incremental or they can be quite radical. This change from Leviathan to Cthulu was done to reduce the overall size and weight of the robot, while adding additional space for having flexible attachment of actuators. The changes in the subsequent year were just incremental, changing the way that the buoyancy is balanced on the robot and increasing the overall size to, again, increase balance and modularity. The changes that we then made between 2020 and our 2022 competition robot, which is still unnamed, were even more radical than those that happened to Leviathan. Because we switched from a very large sensor called the Workhorse Navigator DVL to a much smaller DVL, many new design possibilities were opened up, which is one of the things that I love about the mechanical team. Things can change, and we have a lot of freedom to design the robot in the way that we believe will be best for performance and competition. Now we'll dig just a little bit more into some of the specifics of what the mechanical team does. As I mentioned before, balancing the mass and buoyancy of the robot is an important part of what the mechanical team does. In order to make sure that it will float and float in a good orientation before it's actually built, we create models of the robot representing the different components with parts of a correctly specified mass and volume, so that we can check to make sure the center of mass and center of volume are approximately co-located in the X and Y directions. We also want the center of mass to be just below the center of volume in the Z direction to make sure that the top of the robot is actually what floats towards the top of the water. Considerations like this are unique to robots that operate in a fluid, like underwater. And this is just one of the many interesting challenges of underwater robotics. Many of the tasks in the RoboSub competition require mechanical actuation in order to be completed. So creating actuators is one of the most interesting parts of robot design, and it's one of the parts that new members generally get to work on first. Pictured here are a marker dropper in the top left, a torpedo launcher in the bottom center, and a grabber claw in the top right, all of which were designed by Robotics Club or mechanical team members specifically for this competition. Like in the overall robot design, mechanical team members have a lot of freedom in creating the best possible versions of actuators. And as you can see in the various versions of the marker dropper here, there are often many different ways of completing the same sort of task. In 2018, a pneumatic piston actuated marker dropper was made to drop golf balls, which were the sort of standard manipulated unit in the 2018 RoboSub competition. In the subsequent years, the team decided to switch to servo actuation, and two different versions of a marker dropper made to dispense metal spheres are shown in the 2019 and 2020 images here. The 2020 image is a new innovation off of the basic 2019 design. For switching back to a pneumatic system in 2022, an even smaller and simpler marker dropper could be made with a custom marker that looks more now like a torpedo than a sphere that the team traditionally used. So the level of innovation that you can see between these years here is a testament to the creativity of our members. Much of the mechanical team's work does involve interacting with and supporting the needs of the electronics and computer science subteams. Perhaps the feature in which this is most evident is the double bore seal at the base of the 2020 capsule. This is what prevents water from coming into the electronics capsule and flooding the electronics, which would of course be a disaster for the robot. Also, some of the most intricate and some of my favorite parts on the robot are these electronics mounts, shown colorfully in the image on the left. They help us make the best use of the often cramped space inside of the main capsule. Fundamental changes to the design of the capsule are actually more common than you might think. Back in 2017, we employed a design in which the entire stack of electronics was removed from the robot every time we needed to switch the battery or make a change to the electronic system. But in 2019, we switched from that to a design in which we remove the outer shell of the main capsule, leaving the electronics attached to the robot. In 2022, we're also switching from an internally mounted battery to one that is placed externally in its own separate capsule, so that we can have two of these battery capsules and hot swap them with the robot, enabling us to change the battery without ever turning the robot off. Also in 22, we are switching from a cylindrical stack design, which the club has been using for a number of years, to a gasket type seal, which we've tested extensively to make sure that it will be reliable, but demonstrates, again, the flexibility that the mechanical team has in making changes. When we actually get to competition, the hope is that the mechanical team won't have to do anything major to the robot. Minor repairs, of course, are possible and were necessary in the 2019 competition, but the job of the mechanical team at competition is largely just to support tool testing and the actual trial runs of the robot in the test facility. One of the main pieces of software that we use in the mechanical team is called SolidWorks. It's a computer-aided design package that is very common in universities and in industry, and is a great program for mechanical engineers to know. We also do a bit of manual and CNC machining, as is shown in the bottom left image there. That's the ShopBot carving out one of the pieces of the structural frame of our 2019 robot called Cthulu. Both of these skills, as well as any others that you'll need in the mechanical team, our leadership will be more than happy to teach you. There's absolutely no experience required to join the mechanical team of the Robotics Club. Thanks for listening to what we do, and I hope that wherever you end up, in the Robotics Club or not, you will enjoy engineering. Thanks.